Alright, so my section is section 3.7, which has to do with the derivatives in natural and social sciences. I'll try to go over some of the big topics like some applications in physics, chemistry, biology, and economics. So let's get started with physics, right? So if we're trying to find the velocity or acceleration functions based off of a position function we are given, we're able to do that using the derivative, right? So if we have, say, this graph, just any position function, and so we have our distance and we have our time. If we take the derivative, we're going to get a line that looks something like that. And the slope of this tangent line is going to be distance over time, which equals velocity, right? And then, so if we take the derivative that we just found and put that on its own graph that shows velocity over time, right? The slope of the derivative of this one, the slope of that tangent line, would be velocity over time, which is going to equal acceleration. And so that's the same as saying we're taking the second derivative of the original position function right there. So what we kind of get from this is that the first derivative is going to give us the velocity, and the second derivative is going to give us acceleration if we are taking the derivative of a position function. So let's do the first problem. Find the velocity and acceleration functions. So that's pretty easy, right? Especially after what we know, that s prime of t is going to equal the velocity function. And so we just take the derivative and we get 6t squared minus 8t minus 8 for the velocity function. And then the second derivative, which is the acceleration function, which is going to equal 12t minus 8. So we have our position function, our velocity function, and our acceleration function, right? We've also got to know what those mean and how to interpret them on a graph. And so here we have the graph of the velocity and acceleration functions that we just found earlier. And so we need to know when the particle is speeding up and when it's slowing down. So how to know when it is speeding up and slowing down? If a particle is speeding up, it's going to have forces, or the acceleration and velocity are working together, acting in the same direction. And that makes sense, right? If you have an object going in one direction, and then you have something else that's providing acceleration, pushing it in that direction, it's going to go faster. So the signs have to be the same for it to be speeding up. So either both positive or both negative, right? If we have something going in one direction, and then we have a force acting in the opposite direction, that it makes sense that it is going to be slowing down, right? Because this force applied here is going to make it harder for this other force to keep going forward, and eventually it might even turn it around so it's going in the direction of the acceleration. So that means if the signs are opposite, then it's going to be slowing down. So our job here is to find when it is speeding up and when it's slowing down on this graph. So we need to find all the zeros. So we have a zero at negative 0.75 or so for the velocity function, right? So anything to the left of that is going to be a positive velocity, right? But it's also going to be a negative acceleration for the particle. So that means it's going to be slowing down on that interval from negative infinity to negative 0.75. And then here, past that, we see that the velocity goes to negative. So we have a negative and a negative, right? Because the acceleration is negative here as well, all the way up to where the acceleration equals 0. So what we see here is that it's going to be speeding up in the negative direction from negative 0.75 to about maybe 4/5 or so. So, and then after that, once the acceleration has gone positive and the velocity is still negative, which is all the way up until 2 seconds, we're going to see that it's slowing down again, right? Because the signs are opposite. And then if we go in past the 2, we're going to see that the velocity becomes positive, and so that means it is speeding up. Now we're going to talk about the use of the derivative in chemistry. One very useful way of using it is in measuring the instantaneous rate of reaction in any chemical reaction. So The example problem that we have here says the concentration of the product NaCl in an aqueous solution can be modeled by the formula f of t equals 2 log t plus 2, where t is time in seconds. What is the rate of reaction after 10 seconds? Okay, so we're looking for the instantaneous rate of reaction at 10 seconds, right? So what we're just going to have to do here is take the derivative of the function. So f prime of t is going to be equal to 2 over t ln 10, right? So then we're going to plug in 10 to that, so f prime of 10 is equal to 2 over 10 ln 10, which then goes to 1 over 5 ln 10. And if we plug that into a calculator, we get that is roughly equal to 0.087. And the units for that are going to be concentration over time, right? And so molarity, so moles per liter, all divided by time. And so that's pretty much all you need to do to find the instantaneous rate of reaction. Alright, so now we're going to talk about one of the big ways it's used in biology, which is measuring population growth at a certain instant. So if a culture of bacteria is found to quadruple in size every hour, then what's the rate of growth at time equals 4 hours if the starting population was 100, right? So we know that we have a function where we're going to have it quadruple every hour or so. So 4 to the x should solve that, right? And then so we're going to multiply it by the starting population, which is 100. And so we have f of t equals 4 to the t times 100. And then since we want to find the instantaneous rate of growth, we're going to just take the derivative. So f prime of t is going to equal 100 times 4 to the t ln 4. And then we plug in the time of 4 hours. So f prime of 4 is going to equal 100 times 4 to the 4 natural log of 4. And so we do that, we get 100 times 256 ln 4. And then when we plug that in, we get a very large number. We get 35,489 bacteria, roughly. Bacteria per hour, since it's a rate. It's always important to pay attention to units when looking at these problems. It will help make what you're solving make more sense to you and to the reader. Lastly, we're going to look at how the derivative is used in economics, and one of the primary ways is to find something called the marginal cost, which is the derivative of a cost function. And so the marginal cost can be used to find the price per unit at a certain unit number x. So this question here is asking us the cost of producing cartons of milk can be found using the function c of x equals 100 plus 0.3x plus ax squared. If the marginal cost of producing the 251st carton is $20.38 per unit, find the value of A. So what we have to do here is, well, we know the marginal cost at x equals 251. So first off, we have to find what the marginal cost function is so we can use that information. So it's going to equal this, and then we know that c prime of x is going to equal $20.38 per unit, which is the same as 0.3 plus 2a times 251 units. Alright, cool. So then we just do a little bit of math and move some stuff around, and we get $20.08 is equal to 502A. And then from that, we can find that A is equal to 0.04. So I have a lot more examples of a lot of different applications of derivatives that I will not have time to show you, unfortunately. But I hope this has given you some insight into how widely spread the use of the derivatives is, and what an impact it has made on all sciences. So thanks for watching.